Okay, sir. We can start.
Okay. Hi friends, welcome you to the ARM course. This is the second session of the ARM based development course. In the earlier session, we covered a good introduction to ARM architecture family, and then how ARM core sells their IPs to other IC manufacturers, and the vendors make the chips based on the ARM core, and they build their product around it. ARM also supplies not only the architecture core, it also supplies all the tools, compilers, assembler, and the debugging tools for the vendors to purchase the core and build the system on a chip (SoC) and use the ARM software tool chain to build an end product. Now, in this session, we will be covering a little bit about Endianness and the conditional flags that are available in general in any processor, and in specific to ARM, we will be covering in this lecture. So this is the detailed plan for this session 2. We know, though we claim that ARM is RISC-based design, there are some deviations, and we will see why there are some deviations and what are their advantages. And we'll just touch upon embedded system hardware and software because ARM is built for this market, and we should have a clear idea of where ARM is used and how the software developed for the ARM runs on the embedded system. Now, to understand the architecture of any processor, the basic requirement is that people should know how the processor is used at the end in a system. So, as a developer, most of us will be writing in a high-level language like C or C++ or Java, it could be. But why do we need to know processor architecture and assembly language? The reason being, if you know the architecture and how it runs and how it executes its own instructions, then we will be a better programmer to write our software either in high-level languages like C or C++, there are some critical piece of code is there which needs to be developed in assembly that could be done also and integrated with the C program or C++ code. So having a good idea of the software tool chain and how various tools work together to develop, build an executable and run it on a hardware is very, very important to be a successful embedded software engineer or embedded hardware designer. So both the hardware and software meet in this embedded world. So people who are in this area should have a good knowledge on both to be a successful engineer. So my intent here to give you an overview of the embedded hardware and software. We are not going into detail of this, but it will give you some flavor and which will help you to understand the processor architecture features and how they map onto the hardware or software part of it. And then we will go into the details of stack, because this is the most important part of any programming paradigm. So let us see how stack is implemented in ARM, and the Endianness is also a very critical piece of information that all of us should be aware of. And of course, the condition codes, when you do an arithmetic operations, what are the results of that and how to interpret them is the most important thing as well. So let us see how ARM deviates from a pure RISC design. If you recall from the earlier session, RISC processors are fixed instruction size and every instruction runs in a single cycle, and they have plenty of registers to operate on, and all the arithmetic operations work on only register operands, and most of the instructions run in single cycle. This is what we learned about RISC. But that is not true in ARM. Some of the deviations are done for some reason. One is to make sure that ARM is suitable for embedded applications, because finally the ARM has to be used in some embedded applications to be successful in the market, and the designers thought about that and took some deviations from the RISC phenomena to incorporate what is needed for embedded application. The most important thing is that whatever the code it generates from the compiler from the assembler, it needs to be no small form footprint that it occupies less number of bytes, so that it can be put into a small ROM or flash without occupying too much of space in the embedded hardware, so that we save space as well as we save the bill of materials for the hardware. So apart from that, ARM processor also includes some high-level application-specific instructions too, and also it needs to support real-time OS. I will tell you what are the instructions that are there, but we will go into the details of them when we study about individual instructions of ARM. So as I said, RISC is a very single cycle instructions, most of them, but some of the ARM instructions are variable cycle execution. It takes variable number of cycles for some of the instructions. And one of the examples is that load store multiple instruction, which is actually helping you to store multiple register contents into memory or recover multiple contents, multiple 32-bit values from the memory into registers. So single instruction takes more cycles based on number of registers are there in them. And swap instruction is another example where a memory read and write happen one after the other without any break in cycle. So if the memory cycle takes more number of instruction cycles, then it could be a few instruction cycles to complete this cycle. But why is it required? It is required for supporting semaphore kind of operations. We will talk about that when we come to the swap instructions in the later section. And thumb mode is another 16-bit mode of ARM, where the code instruction bit is instead of 32-bit it is a 16-bit, and conditional execution is another feature where every instruction, assembly instruction, are executed based on the status of a particular conditional flag. So at this moment, I don't want you to know about everything what they mean, but you need to be aware that though we claim ARM is a pure RISC, there are some deviations to support the embedded application requirements. Now, just briefly touch upon what is inside an embedded system. You might have seen so many examples of embedded systems, and I could say if you are entering into an office and there is an access card you are having a ID and you are swiping that at the door. So it's an embedded system where it reads your card and understands whether who is the person coming into the office, and then it sends the data to a particular central server and verifies that you are the person and you have the credibility and access permissions to enter the office. Then it actuates the door lock so that you can open the door and come into the office. So to do this, a system like this is required. It needs to sense when you swipe the card, and that information what it reads from the card has to be processed by the CPU, and then it needs to send it to the central server through a Ethernet port or maybe a IO port, and then verify that you have access permission to the office, and then actuate the door logs so that it allows you to enter the office. So this is typically a example where a part of the code is written to understand the card, what is the contents of the card, and then send it to the server and get it back. So in this case, the embedded system needs to be reliable, and it should operate on a minimum power because it shouldn't be consuming more power to operate, and there are so many restrictions and conditions for this software to work reliably. One example could be that suppose there is emergency, then the door should be, people should be able to unlock the door and exit from the office. So this kind of events it should be able to handle and reliably. That is very important. Now, some of the requirements that a CPU, which could be ARM, and it should be able to read the sensors from the environment, and it should be able to actuate the different relays or any other control engines or motors or whatever, and then it should be reliable and fault tolerant. And this is a very important. Whenever you see embedded system, they say that it should be able to, even if it fails, there should be a graceful degradation. Even if suppose the access card of the office has failed, it should fail in such a way that it keeps it. If it is to a locker room, maybe it should keep the door locked, where very confidential documents are kept. Or if it is to an office, maybe if there is an emergency, people should be able to come out. So you should make sure that the door is kept in the open state during the failure. So this kind of things need to be taken care of in the real-time system, and the real-time system could be, type control to a car engine control to radar, or even a pacemaker which people wear it on their body. So it should be so reliable and it should be able to react very fast. These are the requirements, and a person developing or designing a processor for this kind of environment, we need to make sure that it supports all those features. As well as a programmer, embedded designer, we need to be very cautious about what we write, how we write our code, so that our software runs most reliably in the embedded system. And this is a typical example of embedded system where ARM processor could be there, and then it is connected to memory through a memory controller, and then it could be connected to a serial port or to a Ethernet to a control server, and then we have other peripherals to keep the system running. And our code, what we develop, is running here, and the whole thing is powered by the power system industry. Now, let us talk about embedded system software. How do you develop an embedded system software? It could be any software, but we are very particularly concentrating on developing software for embedded systems. Here, the first step is to write a software, and it could be a C file, or it could be C++ file, or an assembly file, and it goes through a compiler or an assembler based on what is the input that we give it to those tools, and then they are linked using a linker. There may be a library files provided by the processor developer vendor or the tool vendor to the processor, and then the output is loaded into the particular memory, either flash or memory. Then the CPU starts and it starts executing this code. Now, this is the order. Then let us see what these individual tools do to make our executable running. Take an example of a C code here. I have given you a small 2 instruction line. One count variable is there, which is of type integer, and we are integrating it. Now, when we compile the C code, this part of this source file instruction gets expanded to this many assembly instructions. As you see, I have given the ARM instructions here because this is a C compiler meant for ARM, so it is compiling the C code and generating a ARM assembly. Now, suppose if you are using an Intel processor and then you are compiling, you are having a compiler for the Intel processor, it will compile the high-level language code that you have written and then generate Intel-specific instructions here. So, compilers are always specific to which processor you are compiling the source code for. Now, there is another part of it. Also, you remember that the compiler could be running on a PC or Windows PC, or it could be running on a Unix system, or it could be on a Mac. So, compiler asset is running on any of these operating systems and then generating for a particular target processor. So, if you are running the same code in the same platform, then the compiler is meant for that particular platform. That is, when I say platform, it could be a Windows or a Unix platform. But when you are compiling a code for ARM and then you are trying to run this code on an ARM processor development board or embedded system, then you are not running it on the PC, but you are running the executable on a target hardware. Then that kind of a platform is called crash platform, because you are compiling it on one platform and then generating an executable which is meant for running it on the target platform. the code that you develop, generate here cannot run on the PC that you are running, because PC could be an Intel based PC or the AMD processor running there. So this code can run on only the ARM processor. So that is what it means by cross compiling. The C compiler runs the compiles the code and then generates the OBJ file. Now OBJ file is understandable by the tools, but for a human being to read and understand what exactly this OBJ file means, we need to give a special option there, maybe -s or some option based on the tool to generate assembly code to see what exactly instructions it has put in. So let us not go and try to understand this instruction. Now you will be spending a lot of time in understanding the assembly code in the coming courses, in the coming sessions. What I want you to remember that we should be comfortable with reading through assembly. That is the first important criteria for taking a course like this. But you will find it very interesting, and there is an analogy between from C and how it converts gets converted to assembly will be a very interesting part of this course. Now, after this OBJ files are generated, you may have multiple source files, and then you want to generate only exe file. Then a linter is required to merge them all and then generate the exe code. So this is the flow of a C program. Let us see how a C program finally gets converted to executable, and then it runs on the target hardware. Now this is the typical memory space of ARM processor, where some part of the memory. This is the memory which is outside the processor, and the CPU is accessing this memory through address bus and data bus. So this memory is split into multiple spaces: code, data, and heap and stack. We'll see what each of them mean. You can make out that code is for whatever executable that you have made. That the code part of it will sit here, and then if you have initialized data, that will sit in this portion, and then we'll see where stack and heap are required for your program to run. Now, we are given a small C code. You don't have to understand what is actually this is being done. The thing is, here two functions are called. One is accepting, both are accepting integer variables, and then they increment it. Don't bother about what they do with the incremental value, but just to give you a flavor of how a C code gets run on the hardware. That's the intent of this particular slide. Now, in this portion, we have some memory reserved for stack. Now, you see, now what happened is the program is loaded but not running. Now what happened is you use the loader to load the executable in the memory. Now this is the code part of the executable, and this is the data portion of the initialized data portion of the program that you have written, which is loaded into the memory. We could use different tools like JTAG or any other tool to download your software into a hardware, the memory. It could be, you can assume that this is a development board which is ARM based, and it has got a memory space like this, and then you are downloading the code into this memory. Now let us see, when you start running this code, the execution, as you know, any C program starts executing from main. Now you may wonder, how will this processor know that the main code is sitting in this particular address? So that is the job of a library which is given by ARM or any other processor vendor, so that when you write a C code and we put a main, then the control comes to this main, and then the processor starts running from that instruction. Now when it comes here, you know that the static variable as well as the global variables are already there. I'm not showing the initialized value here, only the variables where they are placed in the memory. Now the control is here. What does it mean is the PC, the program counter of the CPU is pointing here. Actually, when it is pointing at this place, it is pointing at the instructions, the assembly instructions which have been generated by the compiler understanding this C code. So when the control now is here, you can see that these variables are placed here, and the local variable which is created here, the main, is also placed in stack. So I will explain more about stack now. You can now, for that moment, you can understand that any local variables are placed in stack. Now let us see what happens now. Now after, when the control goes into the function, the local variable as a parameter here is also generated. A space is created for it. So stack is going downwards. As you see that it is going downwards and then generating space for the new variables that need to be created based on the control flow. Now, after executing from this function, it comes back to the main and then it is about to enter the function 2 here. So, as you see, when it comes back, the space reserved for j is gone. So, the variable j is no longer in the visibility now, and it is not there. The space created for it is also gone. Now, again, when this function 2 is called, it goes into this function and then generates k variable space for k in the stack space, and then control comes here. When it is in the main, still the int variable I is visible, so that stack space is still not gone. And then when the program exits, the stack has come back to the old state. But you may wonder why it is executable and the variables are sitting here, because that's the job of a OS or maybe some other tool to take care that this code is removed and some other executable code. So I am not showing it that that's why this is not removed. So when the program is running, only there is a life for the program, and then there are variables around, and then when it is sitting as a code, it occupies space in the memory, but it doesn't have any state associated with that. So this is a simple example of how a program, C program or any other high-level language program that you have developed for a processor and how it runs on the development board, the hardware. Okay, now let us see how stack. I told you that stack grows and then again shrinks based on the need. Now this is a typical example which I have taken from this on SOC architecture book. It is similar to what I have shown you earlier. Only difference here is the function 1 is calling function 2 again, and then function 2 it goes into function 2 now. So as you see, at a different point in time, see here T1 it has just not even gone into function 1, and when it is inside function 1 at T2 the stack is used for the function 1, and then in T3 when function 1 calls another function 2, the stack is going down again, because you may wonder why the depth is more here or less here. That's based on the amount of space that is required for local variable or parameters in individual functions. The stack grows accordingly. So the size is increasing as the depth of the function calls increase, and then when they come back from the function 2 here at T4, this space is released, and then when it comes back to main at T5, even the space reserved for function 1 is gone. So this is a kind of stack space growing and coming down as per the flow of the program. Now, why am I talking too much about stack? This is very important because every processor needs to support a stack implementation, because as you all are aware, every program has some subroutines and then parameters, and any high level language needs local variables, space for local variables, all those things reside in stack. So a stack is a last in first out. That means what you put into the stack last will be the first one will be taken care of. But that doesn't mean that you can't access the other elements in the stack. But if you know the location of other variables in the stack, you will be able to access them from the stack and operate on them. Only thing is, when you come out of a function, all the variable space is gone, but you will be able to access all the variables which are inside the stack in a function without any restrictions, because you are accessing the stack by using the memory addresses of each of the variables that are occupied by those variables in the stack, as I showed you about I and j and k variables in the stack. So the stack provides space for local variables, and then whenever a function is called, a new frame is created, as you saw in the previous diagram, that it went down by a fixed amount based on the number of local variables and the parameters being passed. So when they come out of the stack, they release the space. Now let us see that, as I told you, every processor needs to support the stack pointer. So the R13 is a register which is used for pointing at the address where the current top of the stack is found. So this is normally used and is a convention that R13 is the name of the register in the processor. We will talk about it more in the subsequent lecture. And so R13 uses for stack pointer here, and then whenever the data item is pushed, R13 is incremented or decremented based on how the stack grows, and then when the value is removed, the stack R13 is not there. Now we also have heap. This is the data area. Stack is based on the local variable and parameters passed to the function, and this is heap is used for any memory that you need for a program, dynamic memory allocation using malloc or free. This you would have heard about in your C program courses. So the heap space is used for this purpose, and they also grow based on the need and based on the program requirement. And whenever the malloc is used, that particular space is allocated, and then when it is free, the space is freed up, and the program cannot use those pointers for it. And then stack space is typical in an ARM space, ARM programming environment. Stack, and I am going back in the slide, stack goes downwards in the memory and the heap goes upward towards the memory, towards each other. So these are all dynamic requirement of memory of a program based on the usage, and when they meet each other, that means there is a space crunch and the program points after that. Okay. So this is the heap space which is required for a dynamic memory allocation, and then minimum runtime library is used. As I mentioned in the earlier case, how ARM processor or any processor knows that there is a mini program starting in the memory. So that kind of support is required. We don't want the developers to write a code for malloc and free. So these kind of free memory library functions are already implemented for a particular processor and given along with the tools, along with assembler and linker and compiler. The library for which is implementing these functions are also provided. And even to start a program, the entry to the main is also some program is startup code is given along with the library. And then if there is a heap and stack space are interfering with each other, that limit is also verified by software functions. And then there are other additional functions also provided along with the library. Now let us see how stack is implemented in a processor. The address to be used to store a data value in a stack is not known at the time of the program, right? So stack is usually implemented in a linear memory space. As I told you that stack can grow, but it can have two options. Either it can grow towards a higher address, or it could grow towards a lower address. So both options are available in ARM. Though some typical processors may implement it in hardware and then support it in only one. And one good example is the 86 family, where the stack is always going towards the lower memory, and it is specific to the particular implementation of a hardware implementation of the processor. Now, as I told you, R13 is one of the registers which is used for pointing at the location which is top of the stack. Now there are two options available. Either it can point to a place where there's already a value is stored in the stack, or it could be pointing at the place where empty space is there. So I'll give you an example here. This is called ascending and full. That means the stack is growing towards ascending, that means higher address, and the stack pointer is pointing at location in the stack which is full, already is filled with some item. And now when the next stack operation is done on this, we can imagine how it will move. So it has to, it's ascending, so it has to move towards the higher address. and then where will the next item pushed would be in the memory here? Will it be here or here? As I told you, stack grows contiguous space, so it has to be in the next location. So in this address. Now what happens when another push or another data item is pushed to the stack? The pointer moves to this location and another item is pushed to that. Now what happens to ascending and empty? This is implementation where the R13 is pointing to the empty location. So this is very specific to a processor. Now which is better? You can follow any convention because you can see that the number of operations that are done to push an item into the stack is the same, because either you increment the pointer after pushing this item, or you increment it before pushing the item. So based on whether it is pointing at an empty location or the full location, the incrementing of R13 needs to be done anyway for every push operation. So either it is incrementing or decrementing is also it takes the same cycle as far the architecture is concerned, but it is a implementation specific, and we can do it in any way. But ARM processor, as I told you, this ARM is like a IP core. So ARM is integrated with any other processor. They have provided all the options so that when it is integrated with a particular another core, it could be from another processor, or it could be working for a particular application. Then based on the need, the IP core can be configured to program the stack in any way. So in this case, ascending empty, when the next item is pushed, it pushes to this location and then it again points to an empty location. Now what happens when a pop is done? That means when you are taking out an item, it has to decrement the R13 and then take the item out and then keep pointing at the empty location. So whatever was done for putting a data, the reverse has to be done in the same way. Now there is another way of implementing it, which is towards the lower addresses, which is descending and full. It is pointing at a full location where the item is already there, and then it is going to be decremented to push another item into it. The fourth option would be very simple. Now you can see that this is the descending and empty. Now you may wonder, when the processor is coming up in a reset location, what is the stack it follows? So there are some instructions push and pop specific to the stack, and they assume descending and full this configuration as a default, and then it could be used in any way. And ARM has given different instructions for all these four types of stack. Now let us see how who decides which type of stack to be used. In ARM, it is decided by the programmer or assembler by choosing a suitable instruction. So, but the thing is, once we decide on a particular implementation for the whole application, it should be the same. We cannot use one instruction which assumes empty and descending, and then while taking the data out, you assume that you use an instruction which is meant for ascending and full. Then what you push, you may not be getting it from the start. So the flexibility is there, but needs to be taken with a pinch of salt, and we need to make sure that the writer, especially if you are writing an assembly code, you remember that you are using a proper code for both pushing and popping the values into the stack and taking the data from there. So this also supports multiple register transfer instructions, and you could use any of those four type of stack for that. Now, as I told you, we can, while storing and receiving the data, we need to have same type of instructions to be used, and then these are the instructions which operate on stack pointers, which are related to stack pointer, and we will talk about these instructions in the subsequent lecture. Okay, now we have talked about stack. Now let us see what is Endianness means. All of you have heard about big endian and little endian. Now take an example. A CPU is there, and there is a register inside the CPU. We always consider 32-bit content because we are talking about ARM 7, and which is a 32-bit registers inside. So this is typically a 32-bit register. These are the bits 0 to 7 and 24 to 31, and these are the values given in hexadecimal. Now there are two ways in which a register content can be saved in a memory. See, the memory that we use here is a byte addressable memory. That means you save every unit of memory location is byte. Is a bit of byte. So address of 1001 is pointing at A1. Maybe I should have put 1000 and 123. I will fix it here. So because it should be aligned to 0 for a better reading and writing. So assume that the address is at 1000 and then 1 and 2 are the other addresses. Then from the higher, the MSB part of the register is stored in the first location, and then as the increasing addresses, the other bytes are stored. Now, this is one way of storing it. This is called big endian model. And then in little endian, what we do, the processor does is it takes the lower byte of the register, and then that it saves in the addresses. So starting from this address and towards the increasing address, it stores the starting from this byte. Now, which one is better? There is no concrete rule that this could be far better than the other one, but there are from the application perspective, I will tell you how these two are different and how which is useful. But it is specific to a particular processor implementation. So these names are called as big and built. If you don't want to remember that, big means that if you see the particular register value which has more content, because this higher byte is having a more value, right? So compared to the LSB bits. So this is stored first, then it is called big endian. If the lower bytes are stored first, this is called a little endian. Now let us see. Let us have a one question here, and I suggest you freeze the presentation and then try to answer this before seeing the option which is correct. So in this question, what we are trying to say is, if suppose a CPU is writing register content, it wrote in a big endian mode, can it read back that memory content into a register in a little endian mode? If it does, which are options are correct? Will the new content in the register will be different from what was written, or the content will be the same irrespective of what Endianness is used, or the content may be same or different? You are not sure whether it may be the same or different. The fourth option is Endianness may not be the same while writing and reading the contents into the memory. So multiple options could be correct. I want you to think for a while and choose one of them before seeing the correct answer to this question. Option A is correct. The reason being, if the value what is there in the register was written in one Endianness, and if it is not read in the same way, you will be seeing a reversal of what was written. So effectively, if you are writing into a memory in big endian, you better read it in the big endian mode. If you are writing it in little endian, then read it in little endian mode. So then only you will get the correct value into the register back. Now let us see how different processors in the market implement this Endianness. See, these are the product processors from different companies use the big endian mode of saving values from register to memory, and these processors do a little endian way of saving it. There are some processors, our ARM is also here, it supports both. Now, why a processor like ARM needs to support both? As I told you, ARM is a IP core which is given to different processor vendors to build their system along with ARM core. So there is a requirement, maybe application specific, or it could be tied to another processor which is there in the system, and ARM is part of it. So ARM should be able to support both the Endianness, so that in a multiprocessor environment, if some other processor from this family is used in a single board and ARM is part of it, and then it should understand the big Endianness of way of writing and reading from the memory. But if ARM is part of any of these processor family, then it should understand the little Endianness Okay, so it is configurable and power on, and even it could be changed while the program is running. But need to be very careful when what you store. The Endianness used for storing a value is used to read it back so that the correctness of the program and the correctness of data that is read from the memory is achieved. Now, what are the advantages, if at all, in any one of the modes? In big Indian way, it is easier to determine a sign of a number. As you know, in a typical binary representation, the sign bit is at the MSB. The 31 bit, 31 is the sign bit. So, if you remember, big Indian stores the higher part of the byte first in the memory. So, you can just read the first byte of the value and then easily find out whether it is positive or negative based on the sign bit value. So, it is easier in terms of big Indianness if it is followed, and easier to compare two numbers, because the value, if it is an unsigned number and you see that some of the higher bits are 1, that means that value is more than some which are having 0. So if you start comparing the bits from the higher end, you will be able to compare two numbers. And division also starts from the top, so it is easier in big Indian, and it is easier to print because we read it from MSB value. Suppose 4028, the 4 may be part of the higher part of the binary representation. So please don't understand, please don't conclude that these operations cannot be done in little bit. It is only easier in this implementation, but both are equally good in terms of supporting other features, and paired multiplication is multiple multiplication precision numbers are easier in implementation. So let us now jump into other important area of processor architecture, which is arithmetic condition codes. All of you might have seen and must be aware of this. I thought I will take amount of time in this course to make sure that the understanding of these flags are very well understood, so that in the subsequent lectures we could proceed further without any problem. So let us start with the explanation for each of the flags, just to have a continuity. Zero flag, as you are aware, any arithmetic operation, if it results into 0, then this flag is set. In a sign flag, all of you may be aware of, and I am sure you are aware of, sign magnitude form or a 2's complement form. In any form, anyway, the MSB bit is meant for a sign bit. So if that is set, the sign flag is set, and the carry flag is, if suppose you two binary numbers are added, and if there is a overflow from there, the carry flag is set. And overflow flag is little different from carry flag. I would like to make use of this presentation to remove any doubts in these two flags. The overflow flag is meant for signed arithmetic. Let us see how they differ in the subsequent quiz. Please go through this question. Here we are saying that there are 4 flags in the system. Control flags are there. This is negative, and this is 0, and this carry and overflow flag. Suppose if it is a 4-bit ILU and then it is performing the 4-bit arithmetic, I want each one of you to take a presentation and then spend 1 minute or 2 minutes to do this, and then see which of the flags are set or cleared, and then choose one of the options based on what you think is the right option. Now the correct option is this. Now let us see how these flags are set when these bits are added. Now the same problem I have given here. These numbers are the same. Let us try to interpret these numbers, what they mean. As I told you, this is a 4-bit number. This could be extended to 8-bit or 16-bit by just simply copying this sign bit to all the higher bit positions. So whatever you understand from 4-bit is applicable to 8-bit or 16-bit or 32-bit also. Now I want you to fill these values for each of these. If it is unsigned, it will correspond to 13, because you will consider this to be a 8 plus 4 plus 1. But if it is a signed value, how do you convert it? is it a negative number or a positive number? Because this MSB, because it's a 4 bit, remember that. So this is a MSB bit. If it is 1, this is a sign bit actually. So it is a negative value. So all of you are aware maybe I have not mentioned it. In this processor, especially ARM processor and most of the processors use 2's complement as the representation for sign number. So in this case, it is representing 2's complement. So how do you convert this into a negative number? What is this correspond to? It corresponds to -3. How do we do that? You complement all these bits and add 1. What you get is 3. That is because this MSB is 1, you put a -3 here. Now similarly, you do this also, you will get 11 and -5. Now when we add these numbers, either it is added as an unsigned number or it could result in a signed value. Now just do a binary arithmetic, you will get this value. Now I want you to see which are the flags are set based on this. I am saying here 0 is clear, while the result is not completely 0. All 4 bits are not 0, so 0 flag needs to be cleared so that the result is not 0. Now why should the carry flag be set? All of you have done arithmetic, you would have seen that there is a carry flag going out of this addition, so it's quite natural that this carry flag is set in this addition. Now what does it mean? Carry flag is set means this unsigned arithmetic cannot be accommodated within the 4 bits, because you know that 13 plus 11 cannot be accommodated, because maximum what we can accommodate in 4 bits is 15. So it cannot be. So the carry flag is set. That means it is a unsigned overflow. Now you see here the overflow flag is clear, whereas signed bit is 1 because this is 1 and 0 is already 0. You are seeing that, and overflow flag is clear. That means the signed arithmetic can be represented in this 4 bit, which is -8. Now how do we know? Most of you might have got it right, or some of you might have got it wrong. This overflow flag, how it is set. Let us see how it is done. Okay, the answer is here correct, and here you see that this answer is correct and this is wrong. Now the explanation for overflow flag is that it indicates whether the signed result, the signed arithmetic after the operation can be fit into the available bit or not. Here Z is clear because -8 can be accommodated within 4. Now let us see how it is computed. In a typical hardware, when you do arithmetic, if it is a 4 bit arithmetic, this is MSB, and MSB on the 1 bit which is closer next to the MSB is also considered a carry flag. Carry coming from this addition is also taken as an input apart from this carry. Now these two carries are XORed to come up with the overflow flag. So this is the way overflow flag is set. Now anyway, this corresponds to the correct value, but this is a way to see whether overflow flag will be set or not. Now let us see one more example where you see that the overflow flag is set here. So take an example. I want you now, because having seen the previous example, you should be able to fill these values and then the result including these flags, and then you can check whether what you get in your computation is same or not, and if there is a misunderstanding, maybe that we can clear it here. Now all of you might have got it right. This both the values, and either it is signed or unsigned value, both are same because MSB is 0. So both are positive numbers, so it can be interpreted the same way. Now this results in 10, whereas let us see, why do we say the signed value is -6? Now we have to see that the difference in interpreting the number, whether it is signed or unsigned, is different. In unsigned, we consider this also a positive value, and then we say 2 to the power 3 here, and then add this value to 8 plus 2 10. Whereas if it is interpreted as a signed value, we consider it a negative number, and then we do the extract this number from a 2's complement representation. How to represent? Now get the -6 value. Now if you do the arithmetic and then apply the XOR operation that I told you in the previous slide, you will be able to get the values of overflow flag. Now you see that overflow flag is set here. Okay, so the result what you got, 7 plus 3 is 10. In sign representation here, you can go up to 7. You can't represent more than 7 in a sign representation, and what you are getting is minus 6. It's not 10, so it's not interpreted as 10. So overflow flag is set. So basically, overflow flag gives you a indication that whether signed arithmetic was done properly or not, whether we can interpret the result correctly or not. In this case, if overflow flag is set, what you have here as a result for overflow arithmetic is wrong. So this is signed arithmetic, and these numbers are interpreted as unsigned. Overflow flag is irrelevant, whereas if it is signed, the overflow flag is to be considered. Now, how signed and unsigned numbers are interpreted? If it is in a C program, you may write signed int or unsigned int, and based on the variable, whether it is global or local, it is allocated by the compiler in either data segment or stack segment. And then when the arithmetic operation is to be performed, the variable contents are copied to registers and operation is performed inside the CPU. Now, when the CPU is performing the operation, it doesn't know whether it is operating on a signed value or unsigned value. So it depends on the programmer or the compiler. It knows when a particular variable is moved, it knows whether it's declared as a signed integer or unsigned integer, and then it looks at a proper flag, whether it looks at carry flag or overflow flag, to see whether the result what was got after the arithmetic operation was correct or not. So this is the way unsigned and signed integers are handled in a processor. So I urge you to, these are the various conditional code, and we will talk about this in the subsequent lecture, but these are the flags which are checked for particular condition, whether it is equal or not equal, or whether unsigned lower or same. So I urge you to verify whether these flags are correct based on this condition, and which will make your understanding better. So in this lecture, what we have seen is risk design and then how they are represented in embedded software, and we touched upon embedded hardware and software, and then we saw stack implementation in ARM, and we touched upon Endianness as well as the condition codes. So we will be having some last sections associated with this to give you some exercise on how to interpret these flags, and whether, suppose in a program, if you are put if I is greater than or equal to j, if both I and j are unsigned, then which is the comparison we need to do? Unsigned higher or unsigned higher or same. This is the instruction, or this is the condition needs to be checked. That means carry has to be set if it is true, the value that you are comparing. If two values which are being compared are unsigned, then this is done. If suppose two values which are compared are signed, then one of these conditions are checked. You can see that overflow flag is seen wherever there are signed operands are compared, and then you see the carry flag is used where there are unsigned operands are. Now you may have a question whether can we compare an unsigned number with a signed number. That is wrong. We shouldn't be doing a comparing unsigned and signed, because it is like comparing apples and oranges. So we'll see how these comparisons are used in the assembly programming, and how does compiler uses these comparisons according to the variables that you are using. So what you need to understand now is that how these comparisons correspond to these flags. And if you understand this, then in the subsequent lectures when we talk about branch based on conditions, or after the arithmetic operation there is a overflow or not, when you are comparing those flags, Understanding of this will make your programming easier. And if you need to write assembly code, it is very imperative and important that you understand these flags without any doubts. So I think we are through with this session. I hope you understood the basic concept that I have tried to explain here. And in subsequent lectures also we will be touching upon these concepts, but this understanding will help you to understand the subsequent lectures as well as the instructions which are coming up in the ARM architecture. We will be able to understand it well. And thank you very much for your time, and hope to see you in the next section. Have a nice day.